Good afternoon, everybody. Welcome to today's Tech Tuesday. Thank you for joining us for this digital twinning focused event, which tracks the rapidly developing technology journey from industry, academia, and stakeholder investment communities. My name is Luke Willits, and I'm the Deputy CEO of Worcestershire Local Enterprise Partnership. We're a key investment partner in BetaDen, which is a commercial technology accelerator operating here in Malvern. BetaDen continues to support technology entrepreneurs and innovators here, where we are currently in Cohort 5 of the programme. In addition, we're also piloting a clean tech bootcamp, which is being run in collaboration with Wireforest District Council, where we've currently got 7 cohort founders developing a range of innovative new products and services with a net zero focus. Before we finish today, I'll share some information about Cohort 6, the recruitment and other opportunities for engaging with this growing technology community within the county. Before we start and hear from some fantastic speakers today on digital twinning, a couple of quick housekeeping announcements. Today's session will run for 60 minutes maximum. We'll have 3 presentations from some great speakers, some great insights to be shared this afternoon. Then after the 3rd presentation is concluded, we'll have the opportunity for an open Q&A session. So again, if I could prompt people to use the chat function to submit your questions as they occur, and the team will collate them as they go through, and we'll put them to the panel at the end of the 3rd presentation. Make no apologies in delivering 3 presentations today, because the breadth and perspective from all 3 keynotes will combine to position the future and value that this emerging marketplace has to offer. So, digital twinning. The development and adoption of digital twins is set to dramatically accelerate and de-risk innovation across multiple layers of the UK's economy and society as a whole. Today, we will discuss the challenges in adopting the digital twin concept in practice and the process for selection of standards and open source solutions. In addition, we'll provide an overview of the activities of some organisations around these topics in more detail, and we'll also discuss the challenges that arise with multiple standards for the implementation. Now, thankfully, you've not signed up to hear from me on this topic, so without further ado, I'd like to invite our first speaker to the virtual lectern. Neil Cassidy is the Group Chief Information Security Officer at Rolls-Royce, and will further introduce the concept of digital twinning and some of the potential benefits we see now and moving forward. So over to you, Neil.
Thanks, Luke. Hopefully some slides have appeared. If somebody can nod and wave, that would be great. So yes, good, excellent, thank you. So as Luke said, my name is Neil Cassidy. I'm the Group CISO for Rolls-Royce. I also have another role where I lead our enterprise architecture practice. So we've been doing a lot of work around digital twinning and the digital thread within Rolls-Royce. I should point out that this is Rolls-Royce Defence and Aerospace. We don't make cars, so I'll be using kind of gas turbine engines as kind of the vehicle to talk around this. It's an area that Rolls-Royce has been kind of at the forefront for a long time. It's a bit like we've been doing IoT type work for a long time before it got trendy names like IoT. We've been looking at the kind of digital twin for some time before it started to really take off, pardon the pun. So how do we get there? I guess once upon a time we had rooms full of draftsmen drawing, creating the designs, creating the component designs, and that was a really slow process. It took a long time. The feedback was almost non-existent, and that's where we'd go. We would be. We moved on then to kind of model-based systems engineering, where you had quite wide scope but quite low fidelity, low granularity in those models. A model-based design where you'd be down at the very small component parts, very high fidelity, but a small part of the overall thing. And now we're moving on to a full digital twin, which for us, our large engines, for example, have somewhere around 20,000 components on them. So if you consider the amount of data that you need to do digital twinning on something like that, it's absolutely huge. Is that all we need to know? Well, probably not. So if you ask 5 engineers, you'll get 5 different answers to what a digital twin and indeed digital thread is. We think of the digital thread as the entire life cycle. So everything from the initial design and concept through to it being in service and disposal. And that's our digital thread. The digital twin then becomes the part of that overall thread where you've got a real component and the virtual representation of it. And everything that happens to that real component has to be represented in its virtual counterpart. And that's no mean feat to achieve. So in terms of thinking about that, if you went back to the pen and paper time with large rooms of draftsmen, you would go through this life cycle from requirements through to service operation and repair. You just go round and round that loop. But as we get into the world of the digital thread and the digital twin, the connectivity and the feedback from all of those individual parts of that life cycle become huge. So we are trying to create an environment where we can take that real world information about what actually happens to a component, what actually happens to the full system, and feed it back into the design parts of that life cycle, and vice versa. So we are looking at taking real world operational data, where degradation, those kind of things, feeding it back into the digital twin. We're looking at the repair data, how that has occurred, exactly what's been repaired, how it's been repaired, and pushing it back into that digital thread. We're looking at technical variations that come out. Things vary as they go through the life cycle. New components are tinkered with. How does that impact on the performance of everything? We're also then looking at, say, the full assembled system and going, well, okay, the kind of as assembled final system, how's the process performed in actually achieving that? How are we feeding that back into it? Because even down to the environmental conditions that we assemble the final system together will have an impact on its performance. And again, if you get down into our piece parts, so the individual components, one of those 20,000 components that go onto an engine, again, how has that been manufactured? How has that been manufactured in our own internal supply chain and into our external supply chain? So how do we connect ourselves to our suppliers so that we know, for example, how an alloy's been forged and exactly the conditions it's been forged in, because that has an impact on how it's milled and how accurate and detailed we can do the milling, which then has an impact on the performance and the life of that individual component. And if we can pull all of that strand together, then we'll actually make a much better component for our customers. So that's great, but why do we do this? So for us, what we're looking at is things like reducing risk. So I'm sure when everybody finally gets to go on holiday, they'll be delighted that at the forefront of what Rolls-Royce does, we are worried about risk, and we want to reduce that down. So that thing that dangles under the engine, under the wing, and keeps you in the air is spectacularly safe and will keep you safe on your travels. So it's all about reducing risk, and we used it quite a bit at the individual component part when we were creating the electric aircraft recently. So there's a lot of that digital thread and digital twin has gone into creating that, and that has reduced the risk in producing something very rapidly over the last few years. Increased confidence, again, great from a customer point of view, but that picture of that big fireball is actually a blade off test that we have to do for every engine as part of the testing process. We basically have to destroy one, at least one. And if it goes badly, you have to destroy another one. So these things cost about £10 million to do that. So we don't want to do it too often. But as we build that full digital model, and we know how it's manufactured and we've got all of that detail in, we can actually run simulations which cost a fraction of that. And they are now being accepted as, from an airworthiness point of view, that's a valid test without having to destroy an engine. And you can think of the environmental consequences of a destruction event like that. So that's really huge for us. Maintenance. So the Rolls-Royce business model for our engines is powered by the hour. So if the thing's not flying, we don't get paid. So you can imagine the last couple of years have been somewhat traumatic for the organisation. But what that does as a business model is it drives your maintenance. So we've been leading on predictive maintenance for some time, and that really involves being able to understand the failures, understand the wear, understand the degradation, and being able to say, well, at this point, we believe that component in that engine is going to fail. So let's get that replacement on the ground at the airport for when that plane is ready to turn around, and we can fit it without any downtime for the airline and for the engine. And that's absolutely crucial for us. And that was, the more we can get into the digital twin space and the digital thread, the more accurate that can be, the less downtime there is, the more flying time, which is good for the airlines and it's good for us. Training is something that, again, we've dipped our toe into with a digital twin. We do have one for one of our engines. It's one that comes in two parts. So it's too big to be shipped on its own. It gets shipped in two parts. And when it arrives, it has to be put together. We train people around the world now using virtual reality on a digital twin, a very accurate representation of one of our engines, and we train them on it as how to fit it together. So we train people from the UK who are based in Singapore as how to put these engines together safely and in a certified way using a digital twin. But we've only got that for one engine. We need to do it for more. So huge benefit for us and for our customers. And lastly, we can play lots of what ifs. You know, we can, if you've got that digital twin, you can play with how it's the system is put together. You can play with the process. You can play with the component parts. You can tweak it. You can adjust it. You can maximize the performance of it. All in a nice, safe environment without having to do that horrible thing in the top right-hand corner, which is destructive test every time. And that is going to lead to better quality products at a lower cost, which is kind of where everybody wants to get to. So they're all the kind of benefits that we're looking at, but there's also the where next, where you want to go. And to be honest, we're only kind of constrained by our own imagination when we get to this point. So this is a horrible slide I put together. It looks like it's been drawn by my 5-year-old boy, so I apologize for that. But what we're starting to look at is if we can take that real-time information off one of our products whilst it's being in use, and we can put it together with how it was manufactured and how it's been repaired and how it's been overhauled through its life, and how it's degrading and how the components are degrading, we can actually optimize the performance of that product whilst it's being used remotely, which from a efficiency point of view, from a lower emissions point of view, sounds fantastic. I then have to put my other hat on of worrying about the security of these things and being in a plane and having people from the UK or people from Derby being able to change the settings on that engine and tinker with how it's set up and configured whilst I'm flying does worry me quite a lot. So there's other things we need to worry about, but being able to do that would massively impact on the cost of travel and air traffic. So the single biggest cost that every airline has is its fuel. So being able to actually fly the most efficient, optimum way every single time could be an absolute game changer for the industry. But that would only be possible with a full digital twin model in place. So they're the kind of, at that point, I'm gonna stop, because I've managed to do 15 minutes, which is perfect. But also, I think I'll hand over to Marcus, I think, next, who's going to talk a bit more about the standards. But hopefully that's given a bit of an overview as to how, as a large manufacturer, we kind of see the digital twin and where it sits and how we want to use it and the benefits that we see from it, which will be huge from an industry point of view. So, Marcus, I think I hand over to you.
Brilliant. Thank you, Neil. That was fascinating. Again, just a reminder, if anybody does have any questions for Neil, if they could pop them into the chat at this stage, and we'll capture those and come back to them in due course. But yeah, if I hand over now to Dr. Marcus Kaufman from Coventry University, who's going to talk about digital twin standards and open source. Marcus, the floor is yours.
Okay, thanks, Neil, and thanks, Luke. Hopefully, you were able to see my slides. Yeah, great. I will apologize in advance. I tried to cram a lot of information in this 15 minutes. So there will be a lot of detail on these slides in there and quite a few slides. So I'll try to move quite quickly through this. So really what we'll focus on today, from my point of view, I work at Coventry University in the Research Institute for Future Manufacturing and Materials. I lead the Institute for Advanced Manufacturing Engineering. Within our team, we have a group looking at digital manufacturing and digital transformation. So we are very much doing research on standards to influence and to help with the adoption of digital twins in very complex use cases. So akin to what Neil described as the future for digital twins there, where you have a full digital twin that encompasses the entire value chain. So this is going from raw material to recycling, all the companies or actors involved in that process, and all the physical assets involved. So be it the raw materials, the components, the products itself, the people, the manufacturing facilities, and so on. Okay, so today we'll briefly discuss the challenges in adopting the digital twin in practice across this wide range of in a value chain. In particular, the process for selection of standards and the use of open source solutions that are seen as a very good way to accelerate digital twin adoption, particularly across the supply chain, where loads of smaller companies perhaps struggle to buy proprietary software. In addition to that, we'll talk about some of the challenges in regards to selecting different standards and standard lock-ins, as we call them, where you adopt a particular standard, but you cannot move or migrate to a different system, okay? So we'll start with, I guess, our kind of view on what are the key challenges around adopting complex use cases for digital twin across industries and across the value chain. So the first one is around the lack of a common definition and understanding of the digital twin concept. I think Neil rightly pointed out that if you ask engineers across a business, what is the digital twin, you get different responses. The same occurs in academia. The same occurs across industry experts. We were at Hannover Messe last week and we asked loads of experts from different companies, and they all had different definitions of what the digital twin is, how complex it needs to be, but also what the infrastructure required to implement them are. So there is a big risk in here that unless we address some of these issues around the definition and the characterization of digital twins, the term digital twin will be downgraded to just a buzzword and no one will give it any credit. which will be a big shame. The second issue we have is back-end data integration. This is particularly around breaking down the silos that we have within businesses and across industries when it comes to how we store the data. So if you go back to the digital thread that Neil explained, if you think across that digital thread, how many different pieces of software you have and how many different formats of data you have. In order to implement a complex use case of a digital twin, you need to break those silos down, and you need to find a way to create a big data set that is accessible and interactive across the value chain. So that's a big challenge, particularly when it comes to legacy systems across well-established and traditional businesses. And then the final challenge is around standardized information models. And I think what I alluded to in terms of the standardization deadlock. People that use proprietary software will be familiar with that. You use a particular software solution from a particular provider. Down the line, you decide to change software, and it's very difficult to convert your data set. The same can occur with your digital twin models. And if you have a single instance digital twin, if you have a single product that you created and you only use it internally in your company, perhaps it's not a big problem. But when you create a very complex and aggregated model of a digital twin across a value chain, that can be a big, big problem that can cost you millions of pounds. So open source and standardization can help you address those issues. So what we'll cover today is some key areas that can address some of those issues and perhaps enlighten and give you some insights into how you can approach some of these challenges. So as a starting point, I always like to go back to the concept of digital twin and when did it emerge and how does it evolve and continue to evolve. And what we see is from 2003, when we first heard of the words, or the combination of words digital twin, all the way to where we are now, we have seen a massive change on how things are defined, changes in interpretation, evolution of different technologies that can enable digital twins. And all of those are I guess, positive things. It means, the concept is evolving, is getting adopted, is getting tested. But there is not a lot of standardization around definition of digital twins and how we characterize what they actually are. So one way to look at it that we find very useful is to go back to standards. And here we have the ISO standard 23247, which defines digital twins in the context of automation systems and integration, particularly around a digital twin framework for manufacturing. And it talks about three critical elements that I think everyone who works with digital twins will agree. In order to characterize a digital twin or to have a digital twin, you have a data set that might contain data collected from a physical object. You might have, secondly, a digital twin data model or various models, depending on what the digital twin wants to represent and how complex it is. So you can have your CAD data, your CAE data, 3D simulation models, and a number of other submodels there. And finally, you have the service interface for that digital twin. So this is really around how does that digital twin interact with different pieces of software that you have, and how do engineers actually use the digital twin to derive decisions and to arrive at solutions that perhaps they wouldn't be able to arrive at without the use of a digital twin. So the key thing here to take is these three aspects: the data itself, the models, and the interfaces. Now, here at Coventry, we have run a number of projects around creating digital twins, various levels of complexity, from simple products and digital twins at product level to one of our latest projects, look at creating a digital twin and a full closed loop for an entire electric vehicle, which will be commercialized in a model for transport as a service, very much like the pay by the hour engine model that Rolls-Royce have. So there is a similar use case there. based on our experience with our projects and our digital twins, we came up with our own simplified definition of digital twin, and I will explain that in a little bit more detail. So a digital twin for us here is a digital representation of a physical asset that's synchronized at the appropriate level of fidelity to deliver value. Now, the delivery of value here is the key thing. So whatever value proposition your own business have, or your own organization, or your own value chain, you design your digital twin around that. So if we break that definition down, digital representation, by that we mean a representation of a real world asset in a virtual environment through data models and submodels. Okay. Appropriate fidelity, what we mean there is the appropriate required level of realism to portray the digital representation that you want to create to achieve that particular intended output, to achieve that value. Synchronized, it means that the connectivity between the two, the physical and the digital model, needs to be set up to the adequate frequency to transmit and receive data, to adapt and to adjust based on your use case. And then again, value is around the particular benefit to the individual, to the organization, to the process, or the society. So if you, the way I find useful to describe it, if you think about this diagram in the left in there, imagine the gray rectangle in the left is your physical asset. And around that physical asset, we establish some metadata, or some labeling, you can call it that defines what that asset is in a high level. So you have a unique identifying feature of that particular asset. Now, what you can do based on that metadata model is what you have next to it on the right-hand side is a series of submodels that can be as complex or as simple as you would like based on your use case to represent the different features and to characterize the different phases of use of that asset. So you can have static data there around the design of the product. You can have traceability data around the production of the individual product and the subcomponents going into it. And then you can have simulation models that try to forecast and predict what the behavior of that asset is going to look like. Now, it's important to know that once you have that digital representation, once you make it at the appropriate level of fidelity, you need to make sure when you are synchronizing and looking at deriving value from it, that you adhere to the right standards for the different submodels. So what I have on the right-hand side there is just an example of the submodels that you could have for different areas within a digital twin, and what are the applicable standards. And that's just a snapshot. It's not all of them. It's just a key summary of those. So just to move on in terms of digital twin solutions, so we understand what the digital twin is a little bit better. We see that since 2020, in the past 2 years, there have been a very big effort by different organizations in terms of creating open source solutions and open source specifications around data models. So I just mentioned a few there of the top names that we worked with before and that we know about, but the list is non-exhaustive. So we have in there the Open Manufacturing Platform, the Digital Twin Consortium, the Industrial Digital Twin Association, the Gaia-X organization, Clean Energy and the Smart Manufacturing Institute, and many others. Now, what all those organizations have in common is they all created standards and they try to simplify the data models and how digital twins are created. So what we have here is a little bit of a benchmark between all of those, because having all those solutions don't help anyone unless you understand them in the context of something that can be meaningful to your business. So if you think about all those organizations and the different aspects that you need to consider for a digital twin across the top, and then you mark based on what sort of extent of activity each of those organizations have, you can create a very simple benchmark matrix, which is what we have on the left there. Now, in particular, based on the work that we do here at Coventry, we have selected an organization that utilizes have been coined back in 2015 as the reference architectural model for Industry 4. For those who never heard of it, is the short for that reference model is RAMI 4.0, and it looks very much like that cube you can see in the middle of the screen there. It is split into 3 axes that try to replicate the complexity of the product life cycle, the organizational layers within a business, and the level of connectivity from shop floor all the way to the connected world. So you can think about RAMI as a kind of bottom-up approach to creating small containers that will have product information or manufacturing information that you can aggregate into standardized bigger containers that will represent perhaps, going from a component to a product to an entire a solution that you offer, or going from a machine to a production line to an entire factory to an entire value chain. Now, in that context, the IDTA, the Industrial Digital Twin Association, utilizes a concept called the Asset Administration Shell. And they developed a whole host of open source software that everyone can download from GitHub and get started on creating digital twin models using that open source software. What you see at the bottom left in there is a screenshot of the open source software that you have. And that's how you create the metadata model and the detailed model that you then can share with your suppliers and customers across your value chain. Now, that gives you a lot of information in terms of the solution, but before you get to a selection and before you go through that decision mechanism, it's very important to think about use cases. How does a digital twin actually aggregate value to your business or to your process or to your team? And I just listed there a number of use cases that are very common with people building digital twins. They start as use cases on the phase of design, they move into the phase of building the actual assets, and then they extend into the as used and as maintained. Normally, a digital twin starting point is the definition of this use case, and then you can move on to a mapping exercise of your legacy systems and existing models, and then move on to the selection of the right standards and the open source tools that you can use. So I cannot emphasize enough that before you select what tools and what solutions you go for, you need to think about the business and the value chain context in which your business operates. What's the purpose and what are the disruptive vectors acting within your value chain, and then formulate your use case. Once you have that use case in mind, we recommend that people use a standard implementation plan. And this is just a sample that we used in 3 or 4 different projects that show you a high-level implementation plan for a digital twin model. And it starts with characterizing what the use case is and characterizing the product or the process related to that particular digital twin use case. Then designing the infrastructure and environment in which you run the digital twin, and then executing that in a pilot environment, evolving it, developing it, and then finally disseminating it across the business or across the value chain, if you like. I know it's a very quick whistle-stop tour of some of these tools, but I wanted to give you a generic idea of where to go. In particular, I want to emphasize the definition of the use case. And here's an example of a standard document that we use here at Coventry in our research center, where we created a template to define a use case based on a standard for use case definition. Very quickly, it goes through what the scope for the digital twin project is, what are the key objectives, ask you some few obvious questions that you should ask yourself, and then finally what the business case is. Document that, share with the collaborators in the project, and is always a good way to start. Just the final 2 slides before I hand over back to my colleagues. If I look at the digital twin use cases across the value chain and some of the key challenges, I think there is a lot being said about the technical challenges. I don't want to dwell on those too much. What I want to focus on is the challenges around business and transactional issues. In particular, the definition of economic impact of digital twins. I think Neil touched upon how much can be saved if you just avoid the non-destructive testing that is required in airspace, but the same would apply to automotive and other areas. So understanding that economic impact and the return on investment from creating digital twins is really important. Understanding issues around intellectual property and cybersecurity, also very important. The more you rely on those models, the more risk, I guess, you run. So you need to be very careful on how those are set up, what environments, and how you protect. Contractual agreements and data ownership, another very important issue that people are just becoming aware of. And then finally, cultural issues. So the definition of terminology, the semantics, and everything else associated with how we characterize digital twins is a big challenge. Workforce development, skills development and training, and then finally certification and approval. How do you rely on those models to verify, validate, calibrate, certificate products and services is very important. There is a lot to be done in these areas. That's all from me. You have my contact details in there. If you're interested on anything, I'm more than happy to take questions at the end, but you can also email me. Thank you very much. I think I just went over a couple of minutes. I'll hand over to Luke now. Thank you.
Marcus, thank you ever so much. That was great. A great overview there. Some of the tools and techniques for anybody that's considering exploring digital twinning further. I see that we had some questions dropped in the chat already. That's great. Thank you. Again, I would urge you, if you've got any questions following Marcus's presentation, to again drop them in there, and we will come back to those. But now I will hand to our third and final presenter for this session, Greg Cox. Greg, over to you from Mazak Europe, talking about value propositions.
Hello, everyone. My name is Greg Cox, and I'm a Senior Manager of European Sales Engineering at Yamazaki Mazak, UK. For those of you who don't know, I imagine many of you in this presentation already do, but Mazak is a machine tool builder. We are one of the biggest machine tool builders in the world. We've got 7 factories, all of which can produce up to around about 100 machines a month. So digital twinning is a very much part of technology that we've been looking into for, like Neil mentioned, prior to it having the buzzwords of digital twinning. We were invested in this kind of technology to support our customers. So we make the machines, as you can see up in the top right hand corner. There's about 300 different types of machine we actually manufacture, and we are unique in the marketplace because we not only develop our own machine tools, we also develop the controller, so the PC-based controller that actually drives those machines around. Now, what I'd like to talk about really in this session is how we've actually used digital twinning, and one of the key things we felt was a difficulty at the beginning of the process of digital twinning. And that's actually the integration with digital twinning as a value proposition. Now, like most technology companies, we can all become very guilty of discovering a new technology or a new capability of a technology and then rushing into efforts to show the use of that, especially when, like with Industry 4, IoT, digital twins and artificial intelligence, there's a lot of noise about that at the time, and there's an interest in or a need in the market to show that you're in those sorts of zones. And it's very easy to develop that technology without really considering the value proposition or what's value to the customer and how you utilize that technology for your customer. And it's customer, but also customers. And it's important that when you look at things like digital twinning as a provider of the technology, you segment your customers into the different areas, because what's useful for one customer as a digital twin might be completely useless to another. And that's one of the key factors that we've noticed. So out of that, what I'm going to talk about now is 2 ways that from us talking to our customers in different segments, we've actually generated real use cases for digital twin technology. And this does fit widely into the explanation given by Marcus just a minute ago of where you treat digital twins as digital representations of physical assets with enough synchronization or syncopation to give some kind of value proposition to the user. So that's our definition. That's how we define digital twinning technology. So there's two areas that I'm going to go through now. One is our what we call smooth cam AI, and then the other is how we actually gather data from our machines and provision that to our customers to do what they want with. And essentially we say to do what they want with because every customer's use of data in this way is individual. So first of all, this is an applied technology that we've had for over a decade. It's become much more like a digital twin in the last 3 years due to the detailed synchronization of data between our physical machine and the machine that we keep as a digital twin on our office PC. Now, for manufacturing parts, you obviously have to write a program, a set of X, Y, Z, A, B, C coordinates that are driven round a part, and then your best utilization of your high value machine tool is to write those offline. Now, traditionally, those are done with pieces of CAD/CAM software, and the CAD/CAM software writes through a post-processor to the machine, which then interrogates the information and makes the part. The advantages of digital twins is that you're able to synchronize the machine's exact data. So things like fixturing, tooling, parameter sets, the position you put the part in the machine, all of the things that can catch you out when you're actually machining a part and cost you time and setup, you can synchronize and produce offline through a piece of software we call Smooth Cam AI, which is essentially a digital twin of the machine in the office space and is synchronized every time you run a program update. So that's one use of an applied technology of digital twinning. Slightly more traditional in its approach is our gathering of sensor data or information data and transferring that through to areas where customers can use this data to create their own digital twins or their own digital representations of the information. So we strongly recommend using standards, and one of the standards that Mazak has actually adhered to is the standard MT Connect. So this is obviously well known within the machine tool world. We were fortunate that we sit on the board of a number of machine tool builders, over 300 in fact, that sit together over in the US and have regular meetings about how data is going to be sent from machine tools in a standardized format through to systems that can then actually read it. And arrived at this standard, which is regularly updated, there's now over hundreds of standard terms which provide the ability to send data through from the machine tool or from its peripheral components through to this standard output that can then be gathered up and used. So that's something that we really recommend, is the use of this. One of the things that we're slightly getting frustrated with in the digital twin world is the number of dashboards that people produce with this data. Dashboarding alone for every single product can be frustrating to our customers and really isn't necessary. So what we do heavily rely on and we heavily recommend is that our suppliers and the pieces of peripheral equipment that actually join onto our machines facilitate digital twinning in a way that they facilitate data acquisition from their devices, and they allow that to be tunneled securely through a system, our system or their own, up to a cloud where it can be gathered in a database and then accessed by things like Power BI. And I think we shouldn't ever underestimate the ability of engineers, and certainly some of the graduate engineers that come through, to dashboard information individually for organizations. Some of the most successful organizations Mazak's worked with, particularly in the UK, for practical application of digital twinning, have gone to a local university and they've taken on a graduate on a project, on a teaching company scheme or a similar type of project, and they've used that graduate to actually produce the information that is valuable to their business from the outputs they get from their standard equipment. So that's something that we really advocate within Mazak and we really push our organizations to do. producing dashboards ourselves is relatively straightforward. There's tools that you can dashboard data from automatically, things like Power BI. It's very, very easy to do that. And really, it's what you do with the data that's important. So that takes us on to the next stage. And this is, again, some of the applied technology that we've put in place. So there's a couple of examples here. I'm hoping this video may just play now. So what we're actually doing here is we're gathering up the MT Connect data from our machines, and we're able to then simulate that data into a piece of software, standard piece of software like MATLAB, and actually use that to do predictive maintenance. So as you can see up there in the top right hand corner, this is just a machine driving round, and what it's actually doing is it's plotting the standard loads that it would expect in that situation, and using that to look at standard deviations of that load across a broken down section of the machine table and identify things that are out of the normal. So that's the data down there over in the right. So these are the ways that we're working with customers to provide predictive maintenance tasks on our machines. The other applied technology is actually using this standard information output and being able to build up information about the machine's energy usage. So this is obviously a hot topic at the moment, not just for environmental factors, but due to the cost of power now. So we're actually using standard sensor information to build up a clear understanding of the power consumption of the machine, so that we can predict at part level what our customers' programs are actually using in energy, and they can then supply that onward to the rest of the manufacturing chain, so they understand about the parts that are being built into consumer products and what their energy consumption is. And then they can use the digital twin in a package similar to or the same as SmoothCam AI to actually reduce that carbon footprint before making the actual part. So use these systems to actually introduce that. Now, what we do at Mazak is we bundle all of that into a single package. We call that Mazak iConnect, and all of these kind of digital twin functions, everything that allows us to link our machines up to the cloud and produce information, we supply in this package called Mazak iConnect. And we offer both a free version and a connected version, where we've actually securely connected our machines from their data source of MT Connect up to the cloud, where we can do data acquisition and provide our customers with the raw data or dashboarded information. So I hope that gives a very quick overview. Obviously, with just 15 minutes, there's not that much opportunity to go into a huge amount of detail, but I hope that gives a quick overview into how Mazak utilised digital twin technology. Thank you very much for your time.
Greg, thank you. That was great. Thank you to all of our speakers. Tough job to such a big subject, trying to do justice in 15 minutes apiece. I think you've given a lot of food for thought there between you guys. I can see that the chat is alive with questions, so bear with me, and I will I'll chuck these out. So first one up then. So Nick Walker from Cyber Reason has asked, Neil, great presentation. You spoke about the security implications for someone taking control of the plane itself, but in the digital manufacturing process, what do you see as the potential threat for IP theft, compliance, and information integrity?
I mean, that feels like about an hour-long answer in itself, to be honest. And you're hitting on a kind of a subject of the bulk of my job. So I think it's both a blessing and a curse all at the same time. So I think the fact that you've got everything connected together in some way, shape, or form makes it a huge target for both IP theft and integrity of data, which is becoming more and more relevant in this space. It used to be everyone used to worry about IP theft, but actually somebody being able to get into that cycle and change the information ever so slightly has huge impacts on safety and performance and lots of different things. So it's a major concern. On the positive side, knowing that it's all together and it's in one place and it's all connected, you know what you're protecting, so you can do something about it. Whereas currently, all of those systems are spread across an entire enterprise in little pockets. You don't know where it is, and you have to try and protect everything to the same level. So it's kind of 6 and 2 3s. You're bringing it in to be more concentrated. You know where it is, you can protect it. But if somebody does get in, the implications are huge. So it does mean that you've got to, it really starts to drive the stuff in cyber where people have talked about look after your crown jewels. This is going to be your company crown jewels. You know where they are. You need to look after them.
Thanks, Neil. Marcus, I'll turn to you next. So Lawrence from Ionos Cloud has asked, do you think that digital twinning standardization will remain fixed in references ISO and FDIS 23247 standards, or only remain fixed until the digital twin assets require new levels of data details?
Yeah, thanks for the question. I think what we've seen so far is standards that deal with the high level definition. They tend to be more fixed, even though all these standards are constantly reviewed. But when you get to the specifications and the standards that look at the models and submodels and how they are defined, that is absolutely, in flux all the time. So the organizations that we work with, they have specific working groups that are constantly reviewing and developing further submodels and further definitions that can be aggregated to the header standard, if you like. So absolutely, as the technology evolves and develops and new use cases are being developed and tested, the results of those tests will influence the standards for sure. We have seen a lot of migration and change, which makes it very difficult to have a strong business case and a strong case for return on investment if you don't know where the standards are going and you don't know if you're locking yourself out. So the idea of having open source software and open source standards is quite useful in the sense that if you are connected to that open source standard and software, as one gets updated and the other one gets updated and rolled out, everyone gets an update for free without having to invest millions of pounds in overhauling your systems and having to find workarounds to convert and translate data sets into new standards. So I don't think they will remain fixed. And I think using open source solutions is a great way to address that flux of standards, if you like. I hope that answers the question.
Lovely. Thank you, Marcus. I've got one for all the panel now. I'll give Greg the first crack at responding to this one. So do you see digital twinning increasing the licensing model of IP rather than physical asset purchases? That's from a kind of a domestic and an international context there, Greg.
I think it's a really good question. I think one of the things that will come to light as a result of digital twinning is the wider use of servitization business models. So actually licensing IP or pay-per-use type systems do naturally progress from the ability to offer digital twinning. So because not only the organization using the technology, but maybe the organization that manufactured the technology has good insight to its use. So I think I imagine that Neil can give some sort of idea on this as well, certainly with the power by the hour type systems that the Rolls-Royce have rolled out over the years. It's certainly something that MASAC are very keen on looking further into is these servitization business models that basically license IP rather than physical assets.
Thank you, Greg. Marcus, Neil, did you want to add anything to that?
I'll just add a little bit to that. I think as you move away from just buying a physical asset from your supply chain, if you just took that as a particular use case, you need to buy all of the other information that goes with it. So how it was manufactured, the environment it was manufactured in, etc. Some of that will contain IP from those organizations in terms of the processes they've used, for example. Therefore, you're going to have to buy IP or have it licensed to you as part of the procurement of that particular asset. So it's going to have to increase to make this work, because you're going to have IP flowing between different organizations, which is either going to be bought or will be licensed. So absolutely, even if you just look at it through that particular lens.
Thank you, Neil. Marcus?
Yeah, I absolutely agree. I think we have seen an increased interest in manufacturing as a service models, whereby if you have a digital twin that represents the characterization of the product and the process, you can very easily outsource some of those. So concepts like micro factories and local factories have been coined, where someone centrally, let's say someone based in the UK, can design a product, design the process, virtually commission that process, and then sell a license for it to be manufactured elsewhere internationally. So we have seen a massive increase. Dealing with IP in that context is quite difficult because, as everybody probably knows, data sets by themselves are not protected by patents or anything, as robust as a patent. So you need to rely on trade secrets and copyrights, and perhaps database rights. But all of those things are fairly flawed in the sense that once you share them, you lose control over those assets. So I think cybersecurity will become a massive influencing factor here on how IP is traded. And I also think, in retrospect, some of the contracts that we have in place across the value chain, be it automotive or aerospace, are absolutely redundant in the context of digital technology and digital twins, and they need to be reconsidered and redrawn based on these new technologies and the potential risk and reward to businesses. So that's my own experience. So absolutely, IP is going to become more important as it already has since the 80s. I think some of the reports that we all are familiar with show that intangible assets have changed from being 10 to 20% of an overall business valuation to being the other way around, 75 to 85% of the business valuation. I think digital twin just brings it home to us in that sense.
Brilliant, thank you. Folks, I'm conscious of time. There's a couple more questions that I want to get to. We can just deal with those before. I noticed David Sidaway asked a question, but to be fair, that came in before Marcus gave his presentation. So we've perhaps touched on that in terms of the types of data capture that we used and put live information to digital twin. So we'll skip that one and we'll finish with the two that are at the bottom. So first, Greg, if you could pick up the one around from Paddy Fawcett. What's new regarding on-the-fly adjustments where cutter deflections mean actual resultant shapes and tolerances are correct, with the opportunity to come back and remove more material, ? And then a lovely skills one for each of you to give a perspective on to finish, if that's okay. Greg.
Oh yeah, no, I'm there. I caught it just in time. Sorry. So looking at adjustments for cutter deflections, actual resultant shapes, we have actually been working extensively with a university in Germany, Aachen University, on a digital twin project that's quite heavy IP protection on it at the moment. So can't go into a huge amount of detail on that digital twin project, but its pure purpose is us being able to have enough sensors on our machine tool spindle and enough data acquisition to be able to predict on a part cutter deflection and cutter abnormalities that have led to changes in the actual part. And we've been able to reproduce parts to alarming similarity to physically measured parts in doing that. So I think the answer to that is it's still quite academic at the moment, but it's anytime soon.
Thanks, Greg. Conscious, I've just seen a message, my sound keeps dropping up, so I'll speak loudly, hopefully everyone can still hear. Final question to the panel, and Greg, if you want to kick off with this one first, it's the question about skills. Do you think there's a global skills challenge? You guys have talked a lot about how digital twinning is being utilised already and how we see that increasing in the future. Is there a skills challenge coming? What do schools, colleges need to address to prevent that from happening?
I do think there's a minor skills shortage coming. I think there's a number of underutilized individuals within the industry, actually, that there's a lot of skills actually out there, and getting organizations to actually push certainly their new recruits and their graduates into finding these sorts of solutions is one of the key things that needs to be done to help with that skills gap. But I do believe there's a big transition now between people that want to do the engineering type of work where they're actually running a machine over towards the more sort of digital side of things. And that's really matching quite nicely with automation and with this kind of technology coming into play. I think the key thing is to make sure that as organizations, we're open to developing new individuals into this area, as well as the schools and universities.
Thank you, Greg. Marcus, as our resident academic, have you got a view on this?
Yeah, I think we already have a big skill challenge at the moment in terms of engineering full stop, right? So we have a deficit of engineers in the UK, and we have an even bigger deficit when it comes to engineers that have digital skills and understand systems thinking and systems engineering. So I think universities are more aware, and particularly universities that have close relations with industry and they have industrial advisory boards in their courses, they are already changing the curriculum to make sure, you know, when a manufacturing engineer or a mechanical engineer are going through their undergraduate degree, they start to familiarize themselves with the concepts of digital thread, of digital twins, all the softwares and that are available, the solutions available. So when they actually join the market, they start working for a company, they can be the change actors. They can be the people actually helping to facilitate change and transformation and adoption of Industry 4 technologies into those business. But it's a very easy thing to say, you know, that's what is happening. It's very difficult to actually do it, because some of the industrial companies that we work with, they still demanding very traditional, very siloed engineering skills, and sometimes they don't see the benefit on having engineers that know how to code or that know how to deal with complex systems. So yeah, I think there is a challenge, and is going to be more pronounced in the future.
I think if I can just add on to that, I think that's one of the things that we're really pushing and realizing, and something universities and colleges need to realize. Engineers need to be able to code at some kind of level. It's actually now an essential requisite for somebody doing an engineering function to have the ability to write some languages of code and understand coding and its benefits.
Excellent. Thank you, gentlemen. I'm conscious of time. I'll draw a close there. There are a couple of plugs that I just need to make very quickly. Before I do that, I'd like to thank again the three speakers for giving your time, and to everybody who's joined us today, and for the questions. Really insightful and very much appreciated. In terms of the plugs, the Tech Tuesday series will continue in September. He just checks his notes. September the 6th, we have our next Tech Tuesday on the topic of Web 3.0 and AI. So please visit the event page on our website where you can register for your free place at that event. The second plug that I wanted to do was around Cohort 6. So we are now formally opening applications for Cohort 6. So if you are, or you know of any tech startup businesses that are looking for support to accelerate your technology product or service, then please do visit our website. You will be able to apply for a place on Cohort 6 with a package worth up to £50,000 of support in terms of mentoring, access to finance, office space, etc. So all the details are on our website, so please do take a look. And if you want to get in touch, we're trying to build a tech community here in Worcestershire. We've got a physical event on the 23rd of June, very informal. It's not stuffy at all. It's BetaDen beers. It's being hosted here at the Science Park on the 23rd of June between 5 p.m. and 7 p.m. So again, please come down, come and learn a bit more about BetaDen. join this growing network, and we look forward to seeing you there. So with that, I'll thank everybody again for your time. Much appreciated, and I'll see you at the next one. Thank you very much, everybody.